Hello, everyone, and welcome to this technical walkthrough of the Folk Smart Contract Library Audit Competition, which is hosted on Immunify. I'm Ash from Immunify, and I'll be guiding you through today's session. So whether you're new to Folks Finance or already familiar with their protocol, we are very glad you're here and hope this walkthrough helps you get the context you need to participate with confidence. This competition features a flat reward pool of 30,000 USD for identifying uh, vulnerabilities in around 440 NSLOC of smart contract written in Algorand Python. This is, in fact, the first audit competition where we have unlocked the All-Star pool, which is reserved for security researchers who are part of our All-Star program. And we also have introduced a podium pool, which is reserved for any security researchers who rank in the top 3 of an audit competition. I'm happy to introduce and welcome Gidon, who is the technical expert from Folks Finance team. He'll walk you through the design of the protocol, the security considerations, and the key area of interest for researchers who are participating in this audience. Gidon, we can get started. So over to you, and thank you so much for being here.
Yeah, thank you, Ash. I guess I'll just share my screen. Okay, so in the resources section, I guess the first thing to highlight are the available documentation and resources that will be useful for the audit competition. So one thing that we created is this Google Doc, which goes through all the different contracts inside the audit competition and gives specifications as well as design decisions and descriptions of the methods and so on. So I think this will be very useful for the white hats to review as they are going through the code, have this alongside and see whether the implementation matches what's in the description, and also if they're unsure as to why a certain thing is designed a certain way, then they could also refer back to this document, which could help explain those sort of things. The codebase as well, you can find on the GitHub. That is linked. We'll dive into that shortly. Then the last thing to highlight is that the code is written in Algorand Python. So Algorand Python, some people may not be aware of how it works, but essentially it's a partial implementation of the Python programming language that runs on the Algorand virtual machine. We link as well to a resource which explains more about the language itself, as well as examples of how to use it and available functionality the language offers. It shouldn't be too different from what you're familiar with in Solidity and so on. It's just a different way of writing smart contracts. The only key differences to highlight are that you're limited to how the Algorand virtual machine works. So Algorand virtual machine has certain storage mechanisms, such as global, local state storage, box storage, and so on. And you have to use these storage mechanisms inside the Algorand Python implementation. So maybe in Solidity, you're used to like mapping and so on. These things aren't really available in the same way in Algorand Python. Instead, you have to use box storage. We'll see examples of this as we go through the code, but I just want to highlight that specific issue. Okay, I'm going to change what I'm sharing. So I move over to the code. Okay, so I've cloned the repository already, but you can just go ahead to the GitHub and do that yourself. The first thing to review is the README file. So it specifies the requirements you need to start the projects. So essentially, you just need Python and AlgoKit. The AlgoKit you can just find on the Algorand website. And then to install to set up the package, you would need to install on Python, the package is required, as well as on NPM, so you can run the tests. To compile the code, we have 2 commands. One is pre-build, which generates the TL code, which is what the smart contracts compile down into. And also specifications for how you can call the contracts. So these are essentially like the API for the contract. And the last thing that we do is we run their build command to generate the TypeScript clients so that we can actually call the smart contract in a type-safe way. If you run these compilation commands, what you'll get is this generated specs folder. And if you're interested, you can review the compiled TL code directly in here. So if you're ever interested in how it compiles down to, you can look at this TL code. But for now, you can just ignore that. And the last thing to highlight here is that we have a testing suite available as well. And to start the testnet, to start running the test, you need to start a local environment where you can do with algo get local net start. That basically makes sure you have an instance of the Algorand blockchain running on your local machine. And then from that point on, you can just run the npm run test command, and that will run the tests, submitting transactions to this local environment that you have set up. Before we dive directly into the code, just a bit of introduction as to what this audit competition is about. So the idea behind this is that we wanted to design a set of smart contracts, a library of smart contracts, which would help accelerate development of the Algorand blockchain. So the library allows you to focus on the business logic of your code and abstracts away common patterns and security mechanisms. So you can imagine that lots of different projects on Algorand have some version of access control within their contract. And each one of them at the moment are implementing it in their own specific way. But it would be nice if we could standardize this and make this contract available to all Algorand developers so that they could just simply inherit from the smart contract and have that functionality already built into their code, as well as it being audited and the work's already been done for them. So we'll begin by looking at the first set of these smart contracts, which is access control. So access control is very similar to the OpenZeppelin access control contract, if you're familiar with that. And the idea is that it allows you to implement rule-based access control mechanisms. So you could sort of have a hierarchy of different roles where you say that, oh, this admin is able to assign these specific roles, and these roles could assign these other roles, and you can build a whole hierarchy of how you want the access control to be managed. So you could have a super admin, an admin, user, and have this all set up through this smart contract. And the way it works is that we have a mapping, in this case using box storage, between a role and a role's admin. So let's say that we have a super admin which can delegate admin responsibility to other users. In that case, then the children admin would be the role, and then the role admin of that address would be the super admin. So essentially, the super admin has the ability to assign the admin roles to accounts. And then we have another box storage, which specifies which addresses have which roles. If I want to assign the super admin role to my account, then it will be super admin and it will be my address specified. And if I wanted then to grant a role of an admin to, let's say, John, then John's address would be specified here and the role would be admin instead of the super admin. So to grant a role, we have this grant role functionality. And what it does first is that it checks that the sender role is the role admin. So if I'm granting an admin role and its role admin is the super admin, it makes sure that the address which is calling this method is the super admin. Because we've got to make sure that they have the privileges to actually assign this role to people. You don't want anyone to come along and be able to assign the admin role to someone. And similarly, when you revoke a role, you need to do the same thing where you need to have the privileges to be able to assign and revoke that specific role. You have functionality to renounce a role. So if you want to give up the responsibility of being an admin, you could call that yourself and you don't need the parent admin to actually call that for you. You could just renounce that yourself. Another thing to highlight as well is the default admin role. So when you first grant a role to a user, if we go to the implementation of that, so let's say we have the role which is manager. So we have the role manager that we're assigning, and we need to first decide who's going to have this ability to give and revoke this manager role. And by default, we say it's the default admin role. So you can imagine like this is the super user essentially that is set by default. So whenever we grant a new role, which has never seen before, automatically the super user becomes the address which can grant and revoke this role. And why this is important is that this default admin role, whoever has this role assigned to them, they can basically have full control as to whether they can grant and revoke roles. And if you wanted to implement a different security mechanism where you had other roles managing, then you would need to change this default admin role. Because at the moment, by default, it's just the super admin always. And you can do that by calling this subroutine. Okay, so here we have the subroutine set role admin. And what this allows you to do is you could assign different admin roles for who can grant and revoke roles. And by default, this is an expose. It's a subroutine, which basically means it's an internal method which can't be called from the outside. So if you wanted to actually call this subroutine, what you would need to do is the contract which inherits from access control. It can expose this subroutine to the outside, or it could just use it as it sees fit. So we can do another example where, let's say you had an Oracle and you have the admin role, Oracle admin. So we have an Oracle admin, and that Oracle admin can give privileges to certain addresses to write prices to the Oracle. So you can call those addresses like price updater role. So the Oracle admin is able to assign the price admin role. So the flow would be that you would first grant the role of Oracle admin. That Oracle admin would have a role admin, which is the default admin role. And then you would grant a role for the Oracle updater to a certain address. And then you would call set role admin, where you specify the Oracle admin, you would specify the updater, Oracle, like the address which can update the prices, that role, so the price updater role. And you'd say that that price updater role should have the admin role of the Oracle admin. So we've moved the admin role from being the default admin role to the Oracle admin. So this is how you can create different hierarchies for various access controls. In addition, I think one thing as well which can be useful to view is that OpenZeppelin's access control is almost identical. There's just a couple changes. So you could review that code and solidity, and that could help you alongside review this code. The last thing I wanted to mention about access control and just this contract in general is that in Algorand, you need to pay for the storage on chain. In like an EVM environment, you may be familiar that just means you pay extra gas when you send a transaction. But in Algorand, it's slightly different, where instead of paying extra costs when you do the transaction, instead, your minimum balance of algo increases. So say you had 2 algo in your account, and you submitted a transaction which increased the storage requirement on chain. In that case, then the Algorand implementation may check to see oh, from now on, you don't need just 2 algo in your account. You need to keep 3 algo in your account until the storage is deleted. Once the storage is deleted, then you can get refunded your money. So in this case, when we create new storage using boxes, the smart contract account needs to have algo to pay for this minimum balance requirement. So this isn't explicitly written in the code, but it's implicitly required. So if you look at like the implementation of the tests, you'll see, I can actually show one of them, where we're doing a funding transaction to the smart contract. So this is paying for the minimum balance needed, in this case, 0.145 algo or 145,000 micro algo. And we're adding that in to the call to the smart contract. So we can pay for the storage requirements. So this isn't explicitly mentioned in the code, but it's implicitly required because the transaction wouldn't work unless you had this funding transaction included. Okay, I think we can move on to the next contract, which is initializable. So the initializable contract essentially just allows the contracts which inherit from it to be initialized. So you're familiar with when you deploy a smart contract on Solidity or EVM, its constructor is called when you first deploy the contract. And similarly in Algorand, when you deploy a smart contract, you have the onCreation method, which is called. Now, what happens if you want to, let's say, upgrade the contract later on? The contract you upgrade to, its constructor or its onCreation method is never called, right? So you sort of want to mimic the behavior of having the constructor onCreation in the contract you're upgrading to. So the initializable contract allows you to do that by having an ABI method initialize, which can only ever be called once. And then once a contract is upgraded, for example, you can set this initialize to false so that the new upgraded contract initialize function can be called. So essentially, you've been able to mimic the behavior of the constructor or onCreation in upgraded contracts. And the other use case for this initializable contract is specific to the implementation of Algorand, where what I was describing earlier, where you need these minimum balance in your accounts to pay for storage on chain. When you deploy a smart contract, you don't know what the address will be. It's not deterministic. So that means that if your smart contract requires some storage and you need to pay for a minimum balance of it, you can't do that all in one go. You can't deploy the smart contract, store some things on chain, because it will find out that it doesn't have enough balance to do that. So instead, you need to deploy the contract, you need to fund it once you know the address, and then you can store things on chain. So this initializable allows you to do that, where initially you would use the constructor or the onCreation method to first get the address of the smart contract. You would then do the funding transaction, and then you would call the initialize, and that initialize becomes basically your onCreation method. So that's the 2 use cases for this smart contract. One thing as well that's important to remember is that this initialize method right now is permissionless. And that's okay, because no matter who calls this method, it's the same outcome, because there are no parameters specified. Like, you're not passing in, who's the admin of this smart contract or who's the owner of this smart contract. That's not a parameter in this initialize method. However, if you did want to inherit from this contract and add additional parameters to your initialize method, then you would want to make sure that the child contract checks who the sender of the transaction is. So we developed an extension for that specific use case called Initializable with Creator. So this inherits from the initializable contract with the added check that the transaction sender is the one who created the contract. And that's to safeguard the case where you have a parameter which you need to pass. So you can see an example here. These are just test contracts, which are used for unit testing. So you don't need to review them, but they're just useful. Okay, I don't think we actually have an example of that. But essentially, if you are to pass parameters into the initialize method, then you would want to ensure that the address is maybe the contract creator or a specific address that you passed that you know of, or so on. Okay, so that's the initializable contract. The next contract we're going to review is the upgradable contract. So the upgradable contract allows you to write a smart contract with scheduled upgrade mechanisms. So in Algorand, they have built into the Algorand virtual machine the ability to upgrade a smart contract. So it's like a specific method you can call to your smart contract. It's known as a allow actions update application. So this means that this method can be used to actually update the smart contract yourself. And this is inbuilt into the Algorand virtual machine. However, there is no mechanisms as to how this upgrade should work. So maybe you want the ability to upgrade a smart contract for the upgrade to be delayed by 1 day. So that's like a common pattern some projects use to ensure the decentralized nature of their smart contracts, where if you had immediate upgrades available, then users may be concerned that you're going to change the logic of the smart contract and potentially like steal funds. So what you could do instead is that you can say that this contract can only be upgraded 1 week in advance. So I need to do a call to the smart contract to say, in 1 week's time, I'm going to change the implementation of the smart contract to a new version. And then users can review the new version of the smart contract, check whether they're okay with it. If they're not, then they can withdraw their funds. But if they're okay to use it, then they would keep their funds deposited, and in 1 week's time, the new version would go live. So that's the use case that this upgradable smart contract is using it for. And in addition, it uses the access control, where we introduce a new role, which is the upgradable admin role, which allows where whichever account has this specific role is able to schedule smart contract upgrades. In addition, it is able to change the delay between smart contract upgrades, or whether it's 1 week in advance, 1 day in advance. This role is able to control those parameters. So like I was saying before, the smart contract has a minimum upgrade delay. So this is how long you need to wait between when you schedule a smart contract upgrade and when it comes into effect. And one important thing to consider is that, let's say the delay is 1 week. You don't want the ability for the address which has this upgradable admin role to set it from 1 week to 1 second, right? Because that sort of defeats the purpose. If they could just immediately set it from 1 week to 1 second and then completely upgrade. So instead, the actual change to the minimum upgrade delay is delayed also by the minimum upgrade delay. So to go back to an example, let's say the upgrade is 1 week at the moment. The time you need to wait is 1 week, and you want to change it to 1 day. So to change it to 1 day, what you would do is you would say, I want to change it to 1 day, but that will only come to effect in 1 week's time. So that means that no matter like if the minimum upgrade delay is changed or not, you know for sure that a contract upgrade can't happen sooner than the current minimum upgrade delay. So this is what this code is doing here, where we essentially have 2 values for the minimum upgrade delay. We have delay 0 and delay 1. And then the timestamp for which determines which delay is active. So maybe delay 0 is 1 week. So, and then you want to change it so that it becomes 1 day. So delay 1 will become 1 day. Now, the timestamp will be when this new delay becomes active. So for now, let's say it's right now it's the 8th of July. So if you were to change it from 1 week to 1 day today, then it will be the 15th of July would be the timestamp for when the new delay will become active. So if the current timestamp is anything before the 15th of July, then a 1 week delay is considered. And if it's anything after the 15th of July, then the 1 day is considered. And this is what this mechanism is doing. The upgradable contract also uses initializable, like I was mentioning earlier, where once an upgrade comes into effect with the complete contract upgrade call, we set is initialized to false. So this means that the initializable methods right here, you can call again. So you can have that behavior of the onCreation method or the constructor being called inside the upgradable smart contract. The last thing to mention is how the contract that you're upgrading to is saved on chain. So the issue is that the smart contract size, the maximum size for a smart contract on Algorand is 8 kilobytes. However, you can't simply save on chain all 8 kilobytes in a seamless way, because the max stack size on Algorand is 4 kilobytes. So if you wanted to, like a naive implementation may just say that which contract you want to update to, like what you're trying to schedule a contract upgrades, and you're saying what contract do I want to upgrade to, and you save all 8 kilobytes on chain. That's going to fail because when you try to save the 8 kilobytes, it's going to exceed the stack size, and it's going to panic. So you could break it into chunks and so on. That's one way to do it. The way we did it is that we take a hash of the various pages of the program. So this is the recipe we're following, where we take a hash of the byte string approval, and then the first page of the approval program, which is 2048 bytes. And then the second page, actually, I think it could be 4 kilobytes. I'm not sure. It's either 2 or 4 kilobytes. And then the second page potentially. And then we take the clear byte string, and similarly we do the pages of the clear program. And then we hash all of that together to get the final program to SHA-256 hash. So when you schedule a contract upgrade, all you're doing is you specify this hash. So you compute this off chain for the new contract you're upgrading to, and you pass it on chain. And then this is just 32 bytes, so we just simply store this on chain without ever exceeding the maximum stack size of the program. Now, when you actually come to complete the contract upgrade, we need to calculate what the program SHA-256 hash is and make sure it matches what you scheduled. So this these lines of code here is doing that, where we're just following the same recipe as we saw above. We have the byte string approval, and we're adding to the program the various hashes of all the program pages. And at the very end, we're hashing the whole thing, so we get a final 32 bytes that we compare to what's saved on chain. And if it doesn't match, then we throw an error. So that's the upgradable contract. The last contract we have is the rate limiter contract. And what this allows you to do is implement rate limiting mechanisms inside your smart contract. So maybe you have like an escrow and you want to make sure that no more than 100 algo is sent per day from your smart contract. So you can implement such a feature using this rate limiter smart contract. And the way this rate limiter smart contract works is that we have various buckets. So a bucket ID is something that the user defines. So it could be like max algo sent, could be a bucket. And then inside a bucket, you have the limit. So how much do you want to consume? What's the maximum amount you can consume? So it'd be 100 algo. So in this case, it'll be 100 e to the 6, because algo has 6 decimals. The duration, so how long you want this to last. So if you want to do 100 algo per day, then the duration would be 1 day in seconds. And then the current capacity and last updated are just used to calculate how much of the capacity is left in the current duration. And the buckets automatically refill. So let's say you had 50% of your bucket consumed and the duration was 1 day. In half a day's time, if no operations happened, then the bucket would be replenished to its maximum. If it was just like 6 hours, 25% of the day, then 25% of the bucket would be replenished. And you can never have a bucket which is has a higher capacity than the limit, right? The limit is the maximum that can be consumed. So if we look at the implementation of this, we also use, actually, no, we don't. All these methods here, they're subroutines. So they're internal methods which are not available to be called outside. Only the reads-only methods are available to be called out from outside. So it'll be specific to whoever's using this contract. They could, like, let's say they want to do a per user bucket. They could have a API method which is like add your own buckets. And that would internally call the subroutine add bucket with the user's address as the bucket ID. So it's ultimately up to the user of the library to determine how they want to call these methods internally. So one thing to highlight is that there's a special case of when the duration is 0. When the duration is 0, then you can imagine that the capacity is infinite, right? Because a duration of 0 means that whatever is consumed is immediately replenished. So another way to understand that is that the bucket has always infinite capacity. So if you look at the implementation of these subroutines, quite a lot of them have this ignore if duration is 0, which essentially means that if you're trying to do a method and it's trying to consume a capacity, then if the duration is 0, then there's nothing really to check, right? Because there's infinite capacity always. So we just early exit if the duration is 0. The last couple of things is that we talked about like the automatic replenishment of when time passes, and that's proportional to the time that's passed divided by the duration. We also have 2 methods, consume amount and fill amount. So consume amount is that when you want to exit from the bucket. So going back to the example where we had 100 algo limit in 1 day for an escrow, if any money going out from the escrow, if you send, let's say, 1 algo out from the escrow, you would consume 1 algo amount inside your bucket. But you may want to do something similar where you're not concerned about how much algo has left your bucket or how much algo has left your escrow. you're concerned about the difference between how much algo has been sent to how much algo has been received. So conceptually, that means what's the maximum amount of algo that I'm willing to send out, considering the algo that I received. So you can have like a starting balance of 1,000 algo in your escrow. And if you were to receive 50 algo in the day, maybe you want the capacity to increase by 50 algo, allowing more to be withdrawn. In that case, we have this fill amount subroutine available, which allows you to increase the capacity temporarily during the duration. And still, we have this check to make sure that you can't exceed the limit. So if the capacity is already hit the limit and you try to pull fill amounts, then it won't actually do anything, because ultimately it's still capped by the limit of the buckets. So that's the rate limiter contract. The last file we're going to look at is this UN64 set library. So this isn't a smart contract, so it's not something you can deploy. It's just various methods available which you can use to implement a set of UN64 values on chain. So these are like utility functions, sort of, or like the equivalent of an actual library on in EVM or Solidity. So we have 3 methods here: has item, add item, and remove item. And this allows you basically to implement a set behavior using an array. So obviously using an array for sets isn't so efficient. So it's not, it should only be used in special circumstances where you specifically need to be able to iterate over the sets. In that case, then you can have these methods available to use. So to check whether an item is inside the set, what you need to do is that you're iterating through the entire array. We considered making like the array ordered. So the search could be like a binary search or something similar, but we just thought the implementation complexity wasn't worth the usage, because anyway, it's quite cheap to do transactions in Outbound at the moment. So this is not a concern for us to do it in a slightly less efficient way. To add an item to the set, what you first need to check is you need to make sure that the item is not already inside the array. So what we're doing here is we're just looking through every single item in the array, seeing if it's already added. If it's already added, then we return false in the array. Otherwise, we add it to the very end of the array. And then lastly, when we remove an item, we need to search through the entire array. So look for the item. If the item is not found anywhere, we return false in the array. And if it is found somewhere, then we essentially take the last item in the array and we write it to the position where the item was found. And that's how we remove the item from the array. And the implementation also assumes that there's no duplicate items, because if you are using this library throughout and you're using add item, then it shouldn't be possible to have any duplicate items in there. Therefore, when we remove item, as soon as we encounter the item, we remove it and we return. And we don't bother looking to see if the item appears multiple different times in the array. Yeah, so these are a review of all the various smart contracts we have.
Yeah, thank you, Gideon. I think that was quite detailed. I'm sure the viewers will find these insightful. So starting with questions, I just wanted to check. So yeah, I know you focused on some of them, these already, but which are the most important areas you feel that a security researcher should focus on, specifically from a point of view of looking for bugs, and why specifically these areas?
Yeah, so we have a number of, like, the audit competition divides the various bugs into categories, and the most important to look at are the critical bugs, right? So the critical ones are making sure that privilege operations are protected. So things like if you're making sure that you can't override the rate limits, right? Only the admin can set the appropriate rate limits. And similarly, only a certain address can upgrade a smart contract, and it's not just callable by anyone. And on that theme as well, one thing to check is that you can't escalate your own privileges. So let's say you had some role assigned to you, there has to be a way, there has to be protections and safeguards in place so that you can't climb the hierarchy and get higher privileges than you should have. So that's the two areas which I think are the most important to look at.
Sure, thank you. That's insightful. And where do you feel there is some out of scope code that can be confused to be in scope? Is there any specific area there?
Yeah, so one thing is that these are a library of smart contracts, right? So it's ultimately up to the developer who's integrating with a library to use these smart contracts appropriately. We want to design it in a way where the risk of the person integrating is as small as possible. But ultimately, if they use it in an incorrect way, they expose themselves to a vulnerability, right? And we don't have control as to how they use the library. We can only push them in the right direction. So one thing is that how they use a library is to some extent out of scope because we don't have control as to whether they use it in the way that's intended. In addition, like the Argo compiler is an external dependency where ultimately the TL code is being run on our virtual machine, not the Python code that we went through. So if there's some sort of bug in the Algorand compiler and the code isn't what you expect, then that would also be something external.
Okay, makes sense. In fact, that was my next question about the external dependencies, but thank you for throwing some light on that. And I believe you also, there is one specific known issue, right? So could you kind of elaborate on that as well?
Yeah, so what I was saying earlier was that to pay for storage on chain in Algorand, you need to have a certain minimum balance of algo in your account. So this isn't explicitly mentioned inside the code, instead it's implicitly required. So if you wanted to grant a new role, which has not been seen before, there's going to be box storage which needs to be allocated on chain. And for that, the smart contract needs some balance. And the method doesn't check to see who is sending this algo, is this algo there or not? It just implicitly will fail if the algo isn't there. So instead, it's on the user to find a way to fund the algo. Maybe that could be in the same transaction group, they could do it, or they could fund it all initially with a certain allocation. It's just up to them as to how they want to pay for these storage requirements.
So, to our viewers, I hope this walkthrough has been helpful. It's provided you more than an overview of the Folk Smart Contract Library code base, and specifically as to what to focus on during the competition. If you have any follow-up questions, the Folks Finance team is there in the Immunify Discord, and feel free to tag them and ask them questions there as well. And of course, the full competition details are on immunify.com under Explore Audit Competition. So if you have any questions specific to Immunify, please reach out to me as well. I'm also available on Discord. So just to recap, the competition is live now. It's going to run till July 21st. So get your reports in there quickly. It's a 30,000 flat reward pool. And which also includes the All-Star and the Podium pool. And of course, there's no KYC requirement for this. So Gidon, thank you so much, for joining us, sharing these insights, and to all of you who are watching and participating. So we look forward to what kind of findings you come across. And as always, happy hunting.